I think now I start recording. Good. Let's get started. Whatever happened, we keep learning. Whatever happened about the COVID situation, yeah, we keep learning. We should keep learning. Okay. So many students still come to here. I'm very sorry because of I need to record and then at the 10 cents, so I cannot turn on the light here. If you turn on light, I think students cannot see the blackboard. So I'm not gonna turn on light here. Okay, last time we learned about the S matrix and then cross section, and then the principle of the S matrix. It's a short range interaction, superposition principle, unitality. The important one is unitality and Lorentz inverse. We fully use this one to determine the form of S matrix. And then today, and then last time, we found that in particular, so 2 to 2, 2 to 2, or 2 to n, a differential cross section d sigma is equal to 1 over 2 d1 2 d1 minus d2, and then mfi square, and then times d pi. This is called Lorentz invariant. This is equal to something like a product. Okay, product of the EF cube 2 pi cube to EF, and times momentum conservation. That's the Lorentz invariant phase. That's what we found last time. We derived last time. And today, first I'm going to explain the consequence of what is the unitality, consequence and unitality. That's I'm going to explain first. And another consequence is another thing is the much more interesting part is how to evaluate this guy. How to evaluate this guy. That's what I'm going to do. Okay. So last time, we talked about the S matrix is the 1 plus this vector. So this is a non-trivial matrix element, and this is without interaction. This is without interaction. Without interaction. So therefore, it's essentially delta Fi. So the initial state and the final state is the same. So we are considering some interaction initial state I to F, but sometimes there's no interaction, so that the initial state and the final state are the same. So therefore, we just exclude such a possibility from initial and final are the same. But the most interesting part is the interaction in between, from the past infinity to future infinity. And then, so what I'm okay, still people come. That's good. So we would like to understand the consequence of this unitality. So unitality is in fact can be understood as the S dagger. Let's see, Sn. So it's a matrix. I and F are the some element in the Hilbert space. I and F are Hilbert space. So therefore, it's a really big. It can be understood big matrix. If I'm in some the entry in some matrix, so therefore, this is essentially means sum of n S and F. It's delta F. Oh, sorry, Fi. I think if I make a lot of mistakes, students can as well. So this unitarity means that this guy. It can be understood as sum over n. N is the n runs all possible Hilbert space. And then plug this one into here. And then you can easily see that this will lead you to the following thing. M Fi minus M star IF is equal to I times 2 pi to the fourth sum over n. This is schematic, and the product, it's a bit hard notation. Product of n, sorry, integral d n delta O df minus sum over I m times n f n and yeah, I think probably I should write down like this. It's hard. Yeah, probably I should write down like this way. Fi and then Ni. So if you plug this equation into here, essentially 1 plus T Fi, and then 1 plus T. Sorry, maybe I should write down I and minus I Fi star. So that's what I'm doing essentially. Maybe I should N and R. Okay. So I call it this one. I call it this one is equal to Ti, Tfi. So this is equal to 1 plus I times Tfn minus T and I star plus let's see. I mean, okay, let's call T and then T star. So that's what I'm doing here. And then this is equal to 1. So that's essentially the meaning of S diagram S, the meaning. And then we just, since we have the 1 is equal to 1, just get rid of it and bring this one into whatever, right hand side or left hand side, and then you will get this equation. So this is schematic form of this T element. T delta 4 times delta 4. So here you have also delta 4, in fact. So this T contain delta, this T contain delta, and this contain delta 4 square. But the overall factor, get rid of overall factor, you get this only 1 delta. So that's what you get from the unitarity. And then, so we like to understand what this equation means. So first of all, I mean, first of all, so if you look at the m can be understood as the something like the some number times. Yeah, of course, we assume that h is equal to h naught plus some coupling constant times hi interaction. So this interaction occurs because of this hi, and g can be understood as a coupling constant. Then this is a coupling constant. Then because of Dyson series, we already know that the m can be understood, and also you did on homework. M can be understood as the some number, some m fi, whatever fi can be understood as the some number times or the plus some number times g plus some number times g squared. Let's see. You can just put up an expansion like this, like this. So that's what it means. So we can do this. So this is the perturbative expansion. Expansion. And then, so if you look at the leading order of this G, leading order of G, so this is actually in the quadratic. So therefore, if you look at the only leading order of G, this will impose the following condition. So here, MFI. So if you look at the leading order of G, MFI, M is equal to M star. Because I mean, if you look at the leading order of G, left-hand side only contain leading order G. But if you look at this quadratic, so you always have the right-hand side is coming from G squared. In fact, G squared. I think. Yeah, sorry. I think there is no leading order. I'm very sorry. There is no leading order because I mean it always, since this is no trivial matrix element, so therefore it always has to include the G. So there is no the dependence G to the 0. So it starts with always from leading order of G. So therefore, so if you only look at the leading order of G, so left-hand side always depends on leading order G, G to the 1. But here, right-hand side always starts from G to the square because it's quadratic. Okay? It's quadratic. Okay? So therefore, if you only look at the leading order G, always this condition is satisfied. So this element has to be equal to 0. So this means that the so the M has to be Hermitian. So if you sandwich, so if you consider this process as the 2-to-2 process, if you consider this kind of process and then consider the following, So this means that the M, matrix M and M, is the imaginary part of P3, P4, M, P1, and P2. If you restrict yourself, this process is 2-to-2 process, and it has momentum P1 and P2 in the past infinity, and the future infinity have a P3, P4. The left hand side is in fact it's just the imaginary part times 2. Is it correct? Yeah, I think so. Imaginary 2 times 2. Left hand side. It's just you just sandwich by initial state is P1, P2, final state is P3, P4, and then so this is left hand side. The right hand side is something like the n and then product of n. So sorry. So this is product of n, and this is Lorentz invariant phase space. Okay, be careful. Lorentz invariant phase. This is pi. This is just product. Be careful about the distinction. Lorentz invariant. This pi, d pi is always this kind of stuff. Okay, Lorentz invariant phase space. I think there is 2 pi to the fourth. I think I missed, and then it's a momentum conservation. Okay, I think it's a momentum conservation. So this is Lorentz invariant space, phase space. So this is Lorentz invariant space. This is product. So be careful. So this is, I should cross. Okay. This impose the momentum conservation. And then P3, P4, M, N. Okay, so that's what if you some initial state is to how to say the wave plane wave function, and the final state is 2 plane wave function, and in middle it can take any Hilbert space in. So this is what it means. So schematically, so this process can be understood as the imaginary, 2 times imaginary. I think I should write down like this. Sorry. The initial state, final state. I see. Okay, anyway, so it can be understood as the sum of n and the product of n, and then we have the 2 process. Any. Thank you very much for bringing eraser. This is much better than this one. Initial step P1, P2, P3, P1, P2, P3, P4. Schematically, you can write down like this. So n in the middle, the Hilbert space can take anything. So n can be anything, any state in Hilbert space, but initial states is sandwiched by any state in the Hilbert space n, and then the final states also sandwiched by any state in the Hilbert space n, and you sum over any state and you impose the momentum conservation in middle. So that's what it means. So this is schematic figure of this equation means. And this form is called optical theorem. Maybe. Okay. Anyway. And in particular, if the f is equal to I, the initial state and the final state is the same, even though there is an interaction between them. This can be understood as the 2 times imaginary part of MII is equal to sum over n and then product of n the Lorentz invariant space m I n squared. So so this is the so therefore since we know the okay. Since we know that the differential cross section is related to by this m, like this way, so I'm going to erase this part. So sigma total differential cross section. So you just integrate over all phase space can be understood as the I to the anything can be understood as the 1 over E center of mass pi sum over n product over n. So this imposes the momentum conservation from initial state to final state. So this is what we already learned last time. We need to integrate over all the final state that impose the momentum conservation from initial state and final state. And then we look at the relation between this one and this one. Then we can conclude that this is equal to 2 times E center of mass pi, sorry, maybe an imaginary part of m pi. Okay. So if you look at this amplitude and you look at the diagonal element and take imaginary part that is proportional to total cross section of I to the anything. Anything means the sum of n, sum of n. So this I means the anything means the any element in Hilbert space. So therefore, you start with the initial state, whatever state, initial state, and then because of this scattering Hamiltonian, interaction Hamiltonian, it can be in final state can be anything, whatever n. Okay. This amplitude, the total different total cross section is indeed, if you look at this amplitude and the imaginary part, is proportional to the cross section. And this is called the whole procedure. I mean, I don't know which one is called optical theorem. Usually people, anyway, usually this one is called optical theorem. So this schematic diagram is called optical theorem. And the consequence of optical theorem is this guy, this equation. And I think many people here already learn in quantum mechanics this kind of optical theorem in undergraduate study. If not, this is the first time. Even if it's first time, it's totally fine. So this is a consequence of the unitarity. So this is consequence of unitarity. Unitarity involves this in opticism. So unitarity of S impose the if you look at the amplitude, imaginary part amplitude, that will give you some differential cross section from the P1 to N and to final state. Okay, so that's the consequence of unitarity. I don't think I have time to talk about the analyticity and then causality of S metrics. So I will skip. I just made in the lecture note, I made a brief comment, but I don't think it's illuminating to go into the detail. So I will skip. So this is the unitarity. Consequence of unitarity of S metrics is the optical theorem. Did you guys learn this optical theorem in undergrad? Some people did, some people doesn't. Okay. Some people did, some people doesn't. But it's okay if you don't learn. So this is the first, even if it's first time. Essentially, optical theorem is a consequence of unitarity. If you look at the imaginary part amplitude, where is it? Imaginary part amplitude, that will give you some information of a differential, cross section. So that's the meaning of the optical. Anyway, so this figure is most important figure. So in the middle, you can cut. So if you take the imaginary part of this amplitude, you can cut in the middle and integrate over. So that's what it means. Okay. Any question at this moment? If not, it's going to a bit more interesting part. So we have been doing so far. We learned free theory, and free theory essentially we just look at the Hilbert space and then obtain Feynman propagator. And then we talk about general theory of interaction and Dyson series, and then theory of S matrix, which is very general, but nothing concrete. And now we are going to be a bit more concrete how to evaluate this matrix element. That's what we are going to do. Okay. Any question at this moment? Okay. Now we are going to learn how to use the Feynman diagram and then compute this matrix amplitude. So once you learn how to evaluate Feynman diagram, you feel like you become physicist. Okay. So now we are going to learn three-level amplitude. So three-level amplitude. First, we are going to learn so we're going to learn Yukawa theory, and then QED. So that's what we're going to learn. First of all, so we try to understand the periodic time ordering and so on. So we learned how to do the Feynman rule for scalar theory. And the Yukawa theory is indeed H is equal to H Dirac plus H scalar or scalar or Klein-Gordon plus G times D cube X G cyber psi. So that's cup HI. So that plays a role of HR. Okay. So these are free theory, and then fermion and scalar field couple in with this term. That's why it's called. This is called Yukawa coupling. This is called Yukawa coupling. So we already knew Feynman rule for scalar theory. I roughly already explained. So we need to understand what's the Feynman rule for fermions. To do that, let us recall that how the time ordering of to get the Feynman rule, we need to understand the relation between time ordering and normal ordering. So we need to understand. Oh, sorry, normal ordering. That was given by weak contraction. Weak theorem or weak contraction. That's what we have learned for scalar theory. So we would like to understand the relation between time ordering and normal ordering in fermions. That's what we want to do. Okay. So time ordering, to do that, we just need to understand that for instance, if you look at the time ordering, psi 2, psi 3, psi 4, and if this is the time ordering x3, 0 is x1, 0, x4, 0, x2, 0. If this is the case, we just need to bring x3 into the front, to the left, and then x4 to the third. So therefore, x3 just bring twice, okay? And then 3, 1, 2, 4, okay? Then x4 to bring one more time. So therefore, you need to, each time you bring, swap the fermions, you have a minus sign. So therefore, you have the minus cube. Psi 3, psi 1, psi 4, psi 2. That's the time ordering of the fermions. Likewise, we need to be careful about the normal ordering. I think I can use here. The fermion creation operator, so normal ordering, if you have this kind of normal ordering, this means that the always normal creation operator to the left, annihilation of the right. So therefore, one has to bring this one into the twice. So therefore, this is minus 132. AQ dagger AP AK. So this is the fermionic. So this is fermionic creation operator. Sorry. Creation. Okay, creation annihilation operator. Okay. So it's not scale. It's not the scalar creation annihilation operator. It's a fermionic. So therefore, you have to impose the anti-commutation relation. So therefore, each time you just swap the operator, you have a minus. Okay. If you want to swap the p and k, you get another minus sign. That's what's written in the lecture note. And in particular, so we already learned oh wow, it's wonderful. So we already learned that if you take the weak contraction like this way, we can take weak contraction. This will give you the final propagator psi plus of x and the psi bar minus of y. As always, x naught and y naught. So plus means the part which contains the annihilation operator, and the minus means the which. I mean, we already learned the free theory. Psi of x can be written dp cube what 2 pi of q to e p squared, and then we have sum over s a p u p plus e to the minus I p x plus a b p. That's it. I forgot. And b e e to the I p x, something like this. I already forgot. This is the Fourier expansion for psi, right? As you recall, this UP and VP is the plane wave solution, and we call this part is psi plus, and this part is psi minus, and likewise the same thing for happen to psi bar. And if x naught y naught is this one, and then here minus psi bar plus of x, and psi minus of y is y naught and x naught, and this is equal to final. If you contract the psi and psi bar, you always have the final property. That's a weak theorem or weak contraction tells you. So therefore, if you have this kind of so what I meant is that this part is psi plus, this part is psi minus. Okay. Be careful about the notation. And likewise, psi bar, we have to do the same thing. Okay. So therefore, if you have normal ordering, psi 1, psi 2, psi 3, and psi 4, if you have a normal ordering, and then take weak contraction, if you want to take a weak contraction like this way in scalar theory. So the difference between scalar theory is that you always bring this one out. So bring out of the normal order, which means that the psi 2 and psi 3 needs to always swapped. So therefore, minus sign will come. And psi 1, psi 3, and we contract it. And normal ordering psi 2, psi 4. Like this way. So always when you take a contraction, you always need to take the neighboring. So therefore, psi 2 and psi 3 is swapped. So therefore, you have minus sign. Okay. So which means that this is equal to minus SF x1 minus x3, and then psi 2 psi 4. So this is the rule for weak contraction of the fragments. This is always a rule of the weak contraction. Okay. So therefore, you take a contraction. So you cannot take a contraction between psi 1 and psi 2 because to get the pion propagator, you always need a contraction between psi and psi bar. Otherwise, it doesn't make sense. Okay, that's a rule. Therefore, whatever. It's always the it's all possible contraction. So that's same as scalar theory. Okay, so that's the same as scalar theory. Okay, so that's a rule for permanence. These are all the general theory, and we are going to apply this general theory to the Yukawa theory from now. Okay. So that's a general theory, but we are going to apply. And first, we want to understand the interaction in leading behavior. Leading contribution. Always coming from HI squared. So HI means that this one, we call it, this one is HI. This is equal to HI. Equal to HI. And so therefore, for in Dyson series, what we need to embody it is that there's something like a leading contribution to 2 to 2, 2 to 2 scattering. 2 to 2 scattering comes from HI squared. So therefore, what we need to evaluate is something like a P prime and a K prime. And then 1 over 2 factorial. So we already know that we need to evaluate 2 factorial. And then minus IG in dipole theory will give you like this term. And then okay, so this time. So 0 means the vacuum of the free theory. 0 means, so PK is really, this is essentially interaction operator, interaction picture. And this P and K is created by whatever. It depends on if it is the electron or electron. It's just created by a dagger. But a dagger, we also use a dagger for scalar theory. So therefore, it's a bit confusing. But anyway, so I will tell you how to evaluate this. For fermions, it's so fermions. For fermions, if you have the sign X operator acts on P and the polarization S, P and S, this is equal to essentially equal to dq prime to pi 2 squared to EP prime, and then sum of S prime and A P prime S prime and U S prime. Sorry, lots of prime. I think it's not good notation. Times I P prime S prime, and then this PS is essentially created by squared EP AP dagger and 0. Okay. Thank you. this is what's the notation. The PS is created by just creation operator and normalized by square root EP. That was our convention. So what we need to do is just like essentially we need to impose the anti-commutation relation here. Then what we have is delta function p minus p prime, and they need to integrate the p prime. So therefore, and this square root EP and square root EP cancel. What's left is this guy. Okay. What's left is this guy. Okay. So therefore, this is equal to. I'm sorry, I'm going to erase here. What's left is equal to e to the minus IP x. Sorry, something wrong here. It should be x. Sorry. X u p and then 0. That's what we have. So therefore, the final rule for this Yukawa theory is as follows. Final rule for you. Final rule. So this we know this. So dotted line, okay, dotted line is always scalar, which means the okay. Sorry, I didn't explain that the Yukawa in 1935, or 30 whatever, 30 mid 30s, Yukawa proposed this the Hamiltonian or Lagrangian, whatever you call it, for the interaction of nucleon. So you have a nucleon, you have whatever nucleon, whatever p or proton or neutron, whichever you call it, and they are interact with the so this let's go n nucleon are interacting by exchanging so-called pion or mesons, whichever you call it. It's a so the so n is represented by psi or psi bar. These are fermionic objects. Nucleon is fermionic object. They interact. They talking to each other by exchanging so-called scalar particle. So I should write down like this way, maybe. Scalar particle. Maybe I don't know. Scalar particle pion. So psi fermion psi bar represents these fermions, nucleon, and then the pion phi scalar field represents pion or meson. And then so therefore this propagator is let's see, it's a p square or q square here. Then I think we already know this is equal to final rule is q square minus m phi square plus I. So this is propagated for a pion. Okay. And then solid line represents the nucleon, whichever proton or neutron, whichever you call it. So this is the we already know p slash m, p square minus m square plus I. That's we already obtained from the free theory. So m phi is the mass of the pion. Mass of pion. M is the mass of nucleon. Okay. So and then because of this interaction, so we have psi bar means that you have this kind of interaction. Okay. So this is equal to minus Ig. Okay. So as you can easily see, minus Ig come here, and psi and psi bar phi will give you whichever psi and psi bar or psi bar psi, depending on you consider nucleon or anti-nucleon that I'm going to explain. So this is some case, and then so external lag. So this is the interaction vertex. Vertex. And the external lag. This is the and the external lag. The important thing is that this will tell you if you contract with like this way, you get that this way. So which means that the psi contract with the P and S polarization. S is a spin polarization. You get this kind of interaction, and then you have P. This is external. This is equal to you get the US of P. So this term will give you just a moment of conservation at the end of the day. So we ignore. Likewise, if you have this is ferment. This is ferment or nucleon or ferment or whichever. And if you have the so this is anti-ferments. So if you have electron, you have a positron, and so on. Anti-ferment, if you contract them, so you have this kind of vertex. And then this is equal to like this. So as you recall, so if you have the so if you have psi bar, so then acts on Ks, then you have TQP prime, you have the same term. And then B bar is, and then it's the same thing story. And times square root to EP, E other SP, that's on T. So that's what we have. Oh, sorry, I think I should call K. Okay. So at the end of the day, we need to we have this guy. At the end of the day, this guy. So you just take the anti-commutation relation B and B dagger, and then you have a delta function, and then at the end of the day you have B. Likewise, you have P and S acts on this is equal to, so this is equal to V bar S E, and then K X. This is of course this is permanent. This is anti-permanent, or anti-nucleon, whatever we call it. And psi, this is equal to sorry, the opposite. Sorry, I told you wrong. this is equal to Vs of. So that's the primary rule for Gauss theorem. Okay. In addition, we need to impose the momentum conservation at each vertex. So that's we need to be careful, and if you exchange, be careful of a sign about when you flip, when you exchange ferments. That's a rule. That's essentially what we need to do. Okay, so that's a general rule, and let's apply this rule to the explicit process. Okay. So first, we'd like to understand the nucleon. This kind of process. So first process is nucleon process. Psi means nucleon. So there are two diagrams that contribute different. So IM, so this matrix element IM is received like this kind of diagram. Okay, so now it's a familiar diagram you always see when you open the book of the whatever physics book of quantum field theory. Okay, the P what was that? The K Okay, have two diagrams that contribute this nucleon process. Okay. And we like to understand how to evaluate this one. So let's first evaluate the first guy. We know pk, and then I have time ordering of half minus ig, and then dx cubed equals psi phi, and then d cubed phi psi phi. Oh, sorry. I think square. I already square it, and then pk. This is what we have. The first diagram. To get the first diagram, what we need to do is that propagator is this guy. So you get the weak contraction of this. That will give propagator of this dotted line. Okay, but anyway, so P is premium. So therefore, what we need to do is need to contract the psi. Therefore, we need to contract psi of P and psi of K. That's what we need to do. And then the external first state is the fermion. It should be contracted with psi bar. Now we contract with psi bar, and then psi. That's the contraction. We'll give you this guy. Okay. To get this guy, you do the same thing, but the different. Let's use different color. I'm not sure you can. The people. Let's use green. Hopefully you guys can understand. So the propagate is the same. Unfortunately, I don't think the students at the 10th can distinguish the color. Okay, let's use yellow, maybe. So the propagate is the same, and the bottom is the same. So therefore, we do the same contraction. Okay, but when you do the contraction, the final state, we do the opposite contraction. So this guy is contract K prime, but here now we contract by P, right? And this guy is contract. That's a difference. So this is yellow diagram. This is the red diagram. Okay. That's the difference between left and right diagram. So the weak contraction is different. So you can see that the I think I made a mistake. I think I made a mistake. Oh, sorry. The opposite. It's totally opposite. Okay, so psi is contracted P, right? And its partner should be contracted be P prime, which means this guy is this vertex is this one, so therefore opposite. Sorry. I'm very sorry. I'm very sorry. I'm very sorry. It's confusing. Sorry. The first diagram, as you can see, easily see, P is psi, and psi bar, this psi bar phi is really coming from this vertex. It will give you this vertex. So therefore, if you contract psi is P, then psi bar should be contracted with P prime, then psi bar is contracted with P prime, which means this contract. So therefore, sorry. So therefore, this is yellow, and this is red. Okay, so this is red. So here, red is psi bar is contracted with K prime. So therefore, the P is contract psi is contract P. So therefore, P and K prime. Okay, that will give you this term. On the other hand, here you have psi is contract K, so that will give you this vertex, and if psi bar is contracted by P prime. So this is this. Therefore, the upper one is red and lower one is yellow. Sorry. Do you understand what I mean? I hope it's clear. And I apply this rule. So therefore, so let's do first yellow. So when you contract yellow, okay, good, I understand. Psi is contracted P and psi contracted K. So the psi needs to bring it to one more. So the psi and the psi bar is swapped. You get the minus sign. Psi and the psi bar is swapped. You get the minus sign. And when you contract first, I mean, psi bar need to contract a p prime. So therefore, furthermore, you need to contract a psi bar and psi bar. This guy and this guy need to swap, okay, to get the contraction p prime. Okay. So what I meant is that the p prime, k prime, and psi bar, and this one is need to contract like first p prime, and the second is contract k. That is a rule. And in fact, psi pk. So this is actually physicists a bit confusing notation. I mean pk should the order pk do not change. So therefore, this guy should contract with this guy. I mean usually it should be k prime p prime. But anyway, so for right hand side you have to contract like this way. First you need to contract p and next k. So therefore first guy should contract a p prime and second guy should contract k prime. That is a rule. So therefore, to contract psi bar and p prime, you need to swap twice, psi and psi bar. So psi and psi bar. Okay, that is automatically do the job that the psi and the k prime. K. Okay. So therefore, you have a -1 times -1, which is +1. So therefore, yellow, this is yellow guy is the minus I G square. And then 1/2 is the symmetry factor that you can swap x and y, so that it'll go on. And then u bar p, u, p. That is really coming from contraction of u, psi and p will give you u, as I mentioned, u, and then psi bar and p prime will give you this u bar. But you have to change this notation. That will give you coming from this part, and then you have another one. So you have a psi contract k and psi bar contract k prime. So therefore u bar k prime and u and k. And you have propagator. Propagated sine phi and phi. That is coming from here, and the momentum should be p minus p prime. Of course, the conservation law. Therefore, it should be p minus p prime square minus m phi. So that's the yellow part. Red part is equivalent, but be careful about the notation. Red part psi is contract p, and psi bar is contract k prime. So what we need to do essentially, psi bar is swap the psi. That's it. No more than that. So therefore, you have overall minus sign. So overall minus sign minus I g square. Oh, sorry. So u is contract of p, u psi bar is contract of k prime. So therefore, we need to have. So this is coming from here. Psi is contracted p, psi bar is contracted k prime. So therefore, one is psi bar will give you this u bar k prime, and the psi will give you up. Okay. And then the same thing happened in the opposite case. And then now here propagated, the momentum is given by p minus k prime. So therefore here p minus k prime square minus m bar square. This is the red part. Do you understand the rule? Do you understand, bro? This is a very important part of the Feynman diagram. Do you understand, bro? So this guy will give you first term is this guy, and then this guy will give you second term. Okay. Psi is contracted by K, so therefore UK, and psi bar is contracted by P prime, so therefore U bar P prime. Okay. And they just you have an inner product. And the phi and phi will give you propagate. Okay. And the momentum is just you just impose momentum function. It should be P minus K. Do you understand? Hopefully you understand. So that's the Wi-Fi. Let's use the just let me check if there is some question from the Tencent part. No question. Okay. Unfortunately, Tencent the color is very hard to see. Sorry, but yeah. Anyway, that's unfortunately the just curse COVID. So now, so we will apply second psi p psi bar k, and then phi and phi. Nucleon, anti-nucleon. So I am the diagram like this way. It's a bit more interesting, right? A bit more interesting than before, hopefully. This is P, and this is K. And then okay, so that's that. So nucleon, anti-nucleon will emit the pion and the pion. That's the process we are considering. Okay, we'll do the same job. Yeah, P K prime. This one T over the half minus IG square D 4 X psi bar psi phi first psi bar psi phi E. Okay. Now let's look at the yellow first. Sorry. So the convention is first one is yellow. So therefore, first P is contracted. It's a fermion. It's a fermion. This is an anti-fermion or a nucleon, anti-nucleon, whatever we call it. And so therefore, phi should be contracted with P prime. Oh, I think the convention is bottom is yellow. Okay, sorry. Bottom is yellow. The phi should be contracted P prime. Okay, that will give you P and P prime. Okay, and what's left is this guy should be contracted with this guy to get the propagator, and then the what's left is just to do the same job. Phi is contracted by K prime, and psi bar is contracted by K. Oh, sorry, I shouldn't use the upper one. Sorry. So the psi bar contract with K will give you anti-nuclear or anti-Fermi. Okay. Do you understand what I mean? Here, psi's contract with P will give you fermions. On the other hand, psi bar is contract with K will give you anti-Fermi or anti-nuclear. Okay. So therefore, the line is like this way, but the moment is the opposite direction. That means the anti-fermions. Okay. Okay. And then second diagram. So we do the same thing, have psi and p, and now k prime, which means that the phi should contract by k prime. And then this guy is contracted by, as always, this one, and psi bar is contracted by k, right? And phi is contracted by p prime. Okay, that's a rule. Okay, and we will do that. Okay. So now also to act psi and p is okay, but to act psi bar to k, so we need to bring psi bar twice, exchange twice, and this guy, psi bar and psi, and the psi bar. So therefore, there's no sign issue occurs. So therefore, this will give you minus I g squared. And then what we have is that the propagator is always fermionic. Okay, fermionic. So therefore, what we have is that the here's what was it? So this is p minus p prime, p minus k prime. Therefore, what we have is that the propagator is in the first term p minus p prime square minus m square, and then p mu and p prime mu and gamma mu and minus m. So that's in the middle. Okay, that's in the middle. And what we need to take a look at is that the psi bar is contracted by k. So therefore, here what we have is b bar k, because here is anti-fermion. What you get is b bar, and then what was it? So this, sorry, this guy is contract p, so that will give you u of p. Phi is insensitive of sign, so therefore, and then just contract with the k prime and p prime, that will give you just momentum conservation. So that's enough. That is yellow. Yellow. And then there's no sign issue because I mean the difference between yellow and red is just how you contract the phi and the k prime and p prime. So that there's no sign issue. That's a plus sign minus ig square. And then the same thing happened. But now the momentum is the propagator here is p minus k. Right? That's that part. Okay? Is that okay? Any question at this moment? Any question at this moment? Is it okay? Are you following? Okay, let's do the last one and then take a break. Last one is indeed that I don't need to change so much. So now anti-permanence. Okay, and I'm going to erase this one, red one, and the yellow one. Okay. Okay. It's a interesting one. Now, so we will do the yellow one first as the convention. So P is always contracted with psi. And now P prime is contracted by this guy. That's very peaceful. Now psi bar should contract with K. Okay, psi bar is contract with K. That will give you anti-fermion. And psi is should contract with K prime. Okay, and then to get the propagator phi and phi are contracted. Okay, they agree? It's already you guys get used to it. Okay, so then red one psi is contract with P. Now psi bar should contract with K prime because P and K prime. So P and K prime. And the same thing happened. So this is anti-fermion, so the psi bar should contract with K. And then now P prime, which means the psi is contracted by P prime. Okay. And then phi and phi. Okay. That is the contraction. And then let's see. So only we need to care about the numerator and the sign. Let's look at the yellow one. Psi is gonna P, and now psi bar need to bring it to exchange psi and the psi bar. Okay, so twice, and the psi bar is contract with P, so therefore psi bar should exchange psi to get the contract with P prime. So therefore you have a overall minus sign. And then what we need to do is that from here, what you get is UP, and the psi bar is contracted by P prime, so therefore P bar. Sorry, U bar. And then here, this one is contracted by this guy, so therefore P bar K. And this guy is contracted with the K prime, so the okay. Now look at the red one. The red one again, psi bar is exchanged twice, and then the sign of psi bar stays the same. So therefore, this is a plus sign. You have U bar K prime UP, and then B bar K and B. So that's what we have. That's the second diagram. Think something wrong right here? Sorry, something wrong. Something. What am I doing here? Sorry, you're right. Oh my goodness. Sorry. I'm very sorry. I'm very sorry. What I'm doing here? Wait. What? No, you channel. Sorry. You're totally right. But it looks to me okay. This one is also allowed, isn't it? This is totally allowed. Sorry, this is definitely totally allowed. I think I didn't include that one. Definitely this is allowed. Definitely this is allowed. Okay, I think this is definitely allowed. Nothing prevents us for this diagram. Oh. Sorry. It's not allowed. Because sorry. We are looking at this diagram. So K prime needs to be sorry. So K prime needs to be anti-nucleon. So this is not allowed. Sorry. What I'm doing. Sorry. This is not definitely true. I'm very sorry. You're right. I'm not careful about. Sorry. Sorry, I didn't take a look carefully about the note. Sorry. Wasting time of you guys. Yeah. So this is okay. This is okay. I'm very sorry. So now let's look at the following procedure. So you have this is red one. The P and the P prime. Sorry. But it's okay. Everyone make a mistake, so it's okay. So here you have K, and then you have the P and the K, and then propagator. Sorry. The bottom one, it should be here, P plus K. Up here, it should be P plus K. And there's no sign issue. It's everything's so peaceful. Everything so peaceful. And from here, you have a UP and B bar K. Sorry, UP and B bar K. And from here, B bar P prime and U K prime. Okay, you understand? Is it okay? Sorry. I'm very sorry about the mistake I made. Is it okay? Let's take a break. If you have a question, just tell me.
I have a question about Feynman description here. Why we omit them in this section? Yeah, here have a Feynman description shapes law.
That I think. I mean, you can include. I mean, whichever. I mean, this is implicit. Everything profit from profits. I mean, just I think I should omit this one because I mean, here everything I didn't include. Right?
Yeah, but actually,
there is a process.
Yes. And another question is that I looked at the Feynman formula as an I. Well, we can add I here, so does it not be?
Oh,
yes, should be an I here.
Oh, you're right. You're right. You're right. I think I should include I.
Yes, because if
yeah, you're right. You're right.
Because
you should include I.
Yes, because
You should
if
include I.
I'm have a real part, this
Yeah,
will.
yeah, yeah. I will after the break. I will include it.
Thank you very much. Another question is not naively about the spin parameter, since we know this search instead. Should be right.
Yeah, that's
space, but we don't know this idea.
Yeah, implicitly here implicitly consider P and K has the S or R parameter. But that is come from S and R.
So it will be right. Yes. Okay.
Oh, there's a question. How to determine the sign of each diagram? I don't know who asked a question, but it's about how to swap the fermions. So you have to be careful about how many times you exchange the fermion. That will determine the sign. I don't know who asked this question, but essentially whatever. This is something. So the n has to be some number one. They have a G squared expansion. If you look at only G, the reading order of G. So this has the something 1 minus something 1 other G. But here, if you multiply them together, it always comes from G. Now, if you only look at the G, leading term has to be equal to it should be equal to 0. Because we only have order. We can only look at the order G. Yes. This should be a plus. Yeah. I would change. Thank you very much. Okay, shall we resume? The bunch of collection. First of all, there's a plus sign here of the plus sign here of the propagator of ferments, and this plus sign here, it should be the case, and the propagator should have a I in the propagator, so you have to multiply I. And here also propagator should have an I, so I, and then previous one should also I. Okay, so that's a collection. Okay, that's how you. I hope you understand the role of the how to apply Feynman rule to treat the global amplitude. This is very important part. So the correction is you have a plus sign here, and each propagator you have a extra I, the I here, the propagator I, you have to include I. So I was not careful about it. Okay. So that's the rule, and then so I will raise the blackboard. The rule for Premium, the one thing you have to be a bit careful is that if you have a loop, if you have a root like this way, the Fermi-Link root, and like this way, so this one will give you is essentially and we just need to contract like this way. So at each point, you contract like this. Contract whatever. 1, 2, 3, 4. Vertex is something 1, 2, 3, 3, 4. Anyway, from now on, I'm going to ignore phi part. And then what we need to do is essentially move this psi bar into the right to the 1, 2, 3, 4, 5, 6, 7. Always number of variables you have to exchange. Therefore, you have -1 trace of psi bar. So that's what we need to do. So therefore, always have a minus sign. So be careful of one. Anyway, even if you add one more external line, essentially what's going to happen is the same. You have to swap the psi bar to move psi bar from left to right, and you encounter odd number of fermions, so you have to have a minus sign. That's one remark. Okay. And then second one, you got potential. So let's consider the following that what we have. It's also like a P prime, K, and K prime. So what we have is this one. This amplitude will give you something like a minus IG I times U bar P, CP, and then U bar. Okay. Minus P prime square plus minus n5 square. That's what we have for this diagram. And then we just need to do the following approximation. So we just take the non-relativistic limit. So the non-relativistic limit is that the P is essentially almost same as P prime, and K is almost same as K prime. So when you have P minus P prime in the so this is essentially the order of P minus P prime to the fourth, and we just ignore this is very tiny, so we just consider this is very tiny. So this is non-relativistic limit. And then we know that if this is assumed, this permanent bilinear. So we have already saw that this one is 2m delta s prime s, and the u bar r prime k prime, okay, is 2m delta k r prime r. Okay. So therefore, if you assume p prime is almost p, so you can impose this one. Therefore, the spin polarization should be the same from initial states to final states p and p prime. That is what it means. S prime and s should be the same in non-relativistic limit. And r prime, R prime and R should be the same. Speed doesn't change. No, let's do it again. And plug that one into the Born approximation. Born approximation, we will get the following thing. The Born approximation is that they essentially a whatever whatever p prime k prime it dk is equal to minus I times p tilde q delta. So this is called Born approximation. Essentially, I think I should include like this way, and also delta prime as k, and q prime. Q is the p minus p prime, like this. And then the plug this one into here. So then this means that b tilde q is equal to minus g square q, essentially. This way. And then to get the potential Fourier transformation, to get this one, it's super easy to do that. This is what you got it in the and the minus g square like this way, and then this one is you can just perform this integral by just using spherical coordinate, and this is equal to now I'm going to omit the detailed calculation 2 pi force by r infinity minus infinity dq q e to the I q r. You just use the spherical coordinate to get this one. From here to here, just exercise. It's just standard way of doing Fourier transformation. And if you pick this numerator, denominator is of course q plus I m q minus I m, right? And if you use the throw the contour in the upper one and pick the pole from here, b of r is indeed equal to minus g squared 4 pi r e to the minus m r. I mean, if you pick the pole from here, it becomes plus sign. But that is like if you go to infinity, the potential is go to infinity. So therefore, you need really infinite many energies. So that this is physical doesn't make sense. Physically, if you go to infinity, the potential goes to infinity. So therefore, you need an infinite energy. So this pole doesn't make physically doesn't make sense. So that we pick just physically from this pole, and this is you call potential. So now, so here you just exchange a pion. Pion has a mass of this is pion. the nucleon exchange the pion. The pion has a mass. So the potential really decays exponentially. It's really quickly. It's a very short range interaction, which means very short range interaction. Okay. Any question at this moment? Then I'm going to QED at tree level. I'm kind of very worried about the I'm very okay. Anyway, so let's move on. I'm not sure if I can explain everything what I wanted to explain today. But anyway, so it's important. For Feynman rule is very important. So it's not bad idea to. Maybe I will omit some of the homework problem in that case if I cannot go to the end. Okay. So QED. Now we will QED at tree level. So the Lagrangian, we already know the minus 1/4 minus, I mean, this is the Lorentz, so the gauge fixing, and then psi bar, I E slash M psi. Now the mu is equal to, so this is covariant derivative. Question? Is it okay? So this is gauge invariant Lagrangian. Okay. So you already showed in the homework this is the gauge invariant in the first homework, and then of course gauge transformation is the mu is mapped to mu plus and the psi is mapped to psi e to the e to the minus alpha, like this way. Of course, everything depends on x. This is the gauge transformation, and it's invariant and gauge transformation. So invariant under gauge transformation. Okay, and let's decompose this term as follows. This is psi I partial mu plus minus e times like this. It can be written like this. And this will give you interaction term. So this is interaction term. Will give you interaction term in QED. So the fermion interacts with the gauge field. Okay. The other part is this is usually free Dirac theory, and this is free Dirac Maxwell theory. Okay, it's just gauge fixing term, and of course, so I always pick the Feynman gauge. So Feynman gauge is C is equal to 1. So this is the Feynman gauge. So this is free Dirac term, free Maxwell term, and this is the interaction term. Okay. So therefore, the Feynman rule is super simple. So the new vertex is essentially this guy. So what we have is the fermion is of course this one is equal to I e slash plus m p square minus m square, and then propagator we already know this is minus g mu, sorry mu and mu. Whatever, whichever you diagram. So my note is like this one. I mean, of course you can put the I epsilon, whatever. I don't like I plus I epsilon anymore. So it's always there. So I'm going to omit. And then so we have a new vertex is this one. This is coming from this guy. And then here and here minus I e gamma mu. So that's a new vertex. E gamma mu will give you minus I e. And the photon is like this way. It's just external photon line is something like a E and the external mu P. So this is photon polarization and the final state. Is the equal to E star. Okay, so that's the final rule for QED. And we will use this rule for a number of times from now on. Okay, I have 40 minutes to explain it. Okay, let's use the following, consider following process that the so if E minus E plus mu minus mu plus E minus E plus P prime. Electron positron goes to muon and anti-muon. So this is the process that we are going to consider. In middle, you have the propagator. Q is equal to P plus by photon. What we want to understand. So now, so then this is the essentially what we have is the let's see, K and K prime K, whichever. Okay, I think my way of writing is a bit strange. Minus 1/2 minus I e squared. And then the x force, the force, and psi bar, have mu, psi and mu, psi bar, and mu, psi and mu, and then p and p prime. So that's what we need to evaluate. So this interaction term really comes from here. Okay. And then, so the way you interact is that the, okay, psi and p, and psi bar and p prime, and then we need k, and then like this. And the propagator will give you like this one. Okay. This is the propagator. And this will give you the process is equal to first of all, so here you have UP minus IE gamma mu, sorry, and then V bar P prime. That's coming from here, and another piece is coming from what was that? And then in the middle you have minus IG mu IOQ square. And then here we have, what was that? Here you contract K, so BK minus I, sorry. I don't have space to write. Oh, wait. So okay, so this is U, sorry. UK prime. No, BK prime, sorry. BK prime minus IE gamma mu. Like this one. So like this way. That's what we have. The first one, UP. This one will give UP, and this one will give a B bar B prime, and in the middle you have a gamma mu, a gamma nu, and minus I epsilon, just the steal from it here. The other one, you have a, if you contract this one with K prime, you have a B K prime, B of K prime, and the sidebar, contract K, you have a U bar K, and then you have a, in the middle, you have a gamma mu, and minus IE steal from here. And 1/2 is just swapping X and Y, so you count. Is it okay? So this is the amplitude you get. Therefore, if you a little bit so the and propagator mu and nu, the propagator here. Sorry, I should write that mu. Sorry, this is nu. Sorry, nu and mu. Okay. So this one, first one is a new vertex, and this one is mu vertex. So I think I should write down the here is the mu vertex. Mu vertex. Okay, that's what we have. And just a little bit simplified. So what we have is I times E square over Q square, and then U bar. I hope you can distinguish U and B in my notation. Oh my goodness. This is U, sorry. And then U bar, okay. That's what we have. Now we want to evaluate the following notation. So you want to evaluate m square. So we want to evaluate differential cross section, and which is proportional to m square. Okay. So to do that, we need to take the. So this is Im. This is Im. As far as I recall, yeah, Im. So that to evaluate this one, you need to take the Hermitian conjugate to get this one. So then what we need to do is that we need to understand so we have this kind of combination B bar, gamma mu, and U, and we need to understand complex conjugate. That's what we need to. And this one is super easy. Dagger, gamma mu, dagger, Okay. And U dagger, gamma mu, dagger, and the gamma 0. So if you take this coordinate, gamma 0 is essentially 1, 1, right? As I mentioned. So therefore, complex conjugate is just gamma 0. So then, and then, so we use the Crewfold algebra. So and the gamma I is sigma I and minus sigma I. If you take a complex conjugate, it's just gamma I dagger is equal to minus gamma I. So therefore, and if you use a Crewfold algebra, gamma 0, gamma I is equal to minus gamma I, gamma 0. If you use this condition, you have a gamma 0, gamma mu, p. Do you agree? Do you agree? So if you do gamma mu is 0, it's just a dagger is just a gamma 0. But if you do mu is equal to spatial I, you have a minus sign. If you take a dagger, you have a minus sign. Dagger is just minus I. But if you swap it, you have cancel the sign. Therefore, you have gamma 0 and gamma. So therefore, this is equal to U bar gamma mu. If you use these combinations, what we'll have is the follows. What we have is that the m squared is equal to e to the fourth q to the fourth. And then, so first one, b bar gamma mu u, the complex conjugate is this one. So you just multiply. So b bar e prime gamma mu u p and u bar p gamma mu b prime and times the second one is the same thing. So second one is the same thing. So we just do the u bar k gamma mu b k prime b bar k prime gamma mu k. That's okay. So here, just implicitly, so the spin polarization implicit. So here, if you have PS S prime and R prime is implicit. This means that here is the S prime, and then R prime. And then, so we have the same combination, S and S prime. What was that? Sorry, S prime, S and S prime. What was that? R and R prime, and R prime and R. Okay, so those spin polarization is implicitly hidden. But usually in experiment, we just cannot the sum of distinguish polarization. So therefore, M, what we need to do is S prime and R prime. We just usually sum of all possible spin. And initial state you can just average over. So therefore, you can, for initial state, the average over the spin polarization, and the final, you just the you cannot measure the spin polarization. We just usually ignore. So you just sum over all possible states. Okay. So therefore, sorry, in this. So this quarter is just average over initial. So therefore, what we need to do is just sum over all possible spin, which means that you just take a trace. So this means that so if you sum over all possible spin here, essentially, so what we have is S and S prime. This means that you just sum over possible spin, and that will give you we already know that this will give you so this will give you let me write the indices. So this is a vector A and B, B, C and CD and D. And we know that this kind of spin bilinear will give you some, so we know that the sum of S, U, and the U bar, and the S, S, and P will give you P slash plus M. Is it plus M or minus M? I forgot. I think minus. No, plus M. And then sum of S, B, and B bar, and P, S and S will give you P slash minus M. That's we already know. So that's you have already derived in homework. So that so this one is indeed becomes trace of P slash minus M and gamma mu and gamma mu. Okay, so that's what we have. So essentially, so the indices here is if you have A and B, you have this is the gamma mu AB and delta AB. That's what it means. Delta AB. So therefore, if you use this formula and provide, if you try to combine this one, sum of all possible spin, sum of all possible spin M square, it essentially means that the e to the fourth 4 q to the fourth trace of p slash minus m and gamma mu p slash plus m gamma mu. That's one thing, and times trace k slash plus m. So sorry, this is e, and this is mu. Okay, plus m mu gamma mu. That's what we have. What are you talking about? Keep talking. So that's what we have. So recall that this here, the bottom part is essentially K and K prime. So therefore, the mass should be mu mass. Okay. The mass, from here, if you apply this rule, the mass should be mu mass. And here, from here, what you get is the electron mass. So therefore, you have to be careful when you take this spin bilinear sum. Spin bilinear. Okay. So that's what we have. Now, we just need to apply the following rule. The important thing is the trace of gamma mu. You already did homework. Is equal to 4 G mu. And trace gamma mu rho sigma is 4 times GG minus GG plus GG. And the indices are what's written in the mu sigma and mu sigma 0. So that's what we have. And then a trace of odd number of gamma is equal to 0. That's what we need to apply for it. Okay. So that's we need to the homework is very important. You already derived this one, and just need to apply for this trace. Okay. Okay. And if you apply this rule, it's super easy. So what we need to do is that the trace. So let's look at this guy. Red part. So red part is equal to. So you have a 4 gamma. If you look at the P prime P part, so just apply the so essentially mu and nu, and let's go rho and sigma, and apply it, and then what we have is that the you have 4 times P prime mu P mu plus P prime mu minus G mu P dot P. That's what we have. That's what we have. From if you only look at the P prime gamma mu P prime sorry P prime slash gamma mu P slash and gamma mu. If you look at the cross term P prime gamma mu M and gamma mu, it's only the gamma matrix involve only 3 of them. So therefore it becomes 0. Odd number of gamma is 0. Okay. So then what we need to look at is M times M and the gamma mu and the gamma mu. That will give you G mu nu. Therefore, what we have is that the minus G mu nu. Oh, sorry. 4 times B. 4 times ME. That's what we have. Similarly, so what we have yellow part, let's go yellow. Unfortunately, I don't think 15 minutes left. The same thing. like this one. So that's what we have. And now you just need to multiply. You just need to multiply. Okay, that's what we need to do. But to do that, so we just notice mu of the electron, that the mass difference is almost like this one. Is equal to 1/200. So therefore, effectively, we can ignore this term. We can ignore this term. I mean, comparing mu mass, electron mass is much smaller. So therefore, sorry, I think it shouldn't write equal, approximately. So you can ignore, and you just contract with these guys. And what we have is that they from here, and the quarter sum of spin and square. Yeah, that's what we have. So this is just a direct calculation one can just obtain. I mean, you can easily see, right? So that's if you contract P prime and K prime, P and K is contracted, will give you this term. And if you contract P prime and K and P and K prime, you get this term. And likewise, it's the same thing. And if you G mean you contract about this one, and this one, and this one, all give you this kind of term, P dot P prime. And you have to be careful about coefficient. That's what we need to do. Okay. So that's the square of this matrix element of the process of this process. This process. So now we want to evaluate this one in center of mass plane. So we know that the d sigma d omega. So d sigma d omega is equal to, and last time we just derived this one is equal to something like a E center of mass square, and then K 16 pi square E center of mass and a quarter of sum of. So this is the formula we found in this center of mass frame. So we just want to evaluate this one in center of mass frame more explicitly. To do that, so we just consider electron E minus is have a momentum P is equal to E times E C hat, and then P prime is equal to E and then the minus is K is equal to E times K vector, and then K prime is equal to E times minus K. So this is center of mass. Okay. So E and E prime, so this is mu plus. Okay. This is center mass plane. Of course, the momentum should be always opposite in initial state and the final state. And the energy should be energy conservation and momentum conservation. You have to import. So therefore, K and K times Z. So this is the angle setter. That is equal to K cos theta. So we will take this kind of the coordinate and plug this momentum into here. It's a very super easy exercise to do that. I'm going to omit that I'm going to omit the computation of this computation. It's super easy, so I'm not gonna write down everything. Plug that one into here, so everything is electional. So you just need to follow a quarter of m squared of spin sum is equal to e to the fourth So this is what's written in the lecture note. I mean, derivation is super easy. I mean, you just follow me to. I mean, I just get you bored if you do the computation. This is what you get. If you plug everything, so this one, I mean, you plug everything into here, and you can just obtain this one. It's super easy. If you plug this one into here, what you get is differential cross section. D sigma d omega. That's the process. Okay, and then you can integrate over d omega. D omega is equal to what was that? Sine theta d theta d phi. I think this is the case. You can just integrate over of this one. Sigma is equal to d sigma d omega. And if you do that, that will give you 4 pi of square is equal to 3e center mass square. I mean, this one is super easy exercise to do this. I mean, I'm not gonna. I mean, if you want to, if you're lazy enough, you just plug in the Mathematica. But by hand, it's also easy to do. This is the total differential cross section. What you get. So alpha is called fine. Do you know alpha? Fine structural constant. And E square 4 pi. HC is hidden, which is approximately 1/137. So that's the okay. So that's the case. And then 5 minutes has left, so I will explain the crossing symmetry. So we evaluate this one. E minus E plus mu minus mu plus, and then P, sorry, P, K, K prime, and E. So if you want to evaluate this kind of diagram, so it's just how to say, just flipped and it's 190 rotation. 90 rotation. What we have is this kind of diagram. E minus, and mu minus, and mu minus, and then this has P2, P1, P1 prime, and P2 prime. So you can easily consider this kind of process. And to get this kind of process, it's easy to get from here to here, in fact. That is called cross-section symmetry. I think I will erase the upper diagram. This process, you can do the same exercise. To do that, this one is equal to I E squared Q squared and U bar P prime P1 prime gamma mu U P1 and U1 U bar to gamma mu and UP2. And in fact, you can easily see it. So here, P1 is like this way, and P1 prime is just the opposite direction of this one. So therefore, what we can do is that from here to here, you can obtain the direction P goes to P1, P goes to P1, and P prime goes to P1, P prime goes to minus P1 prime. Because I mean, here P1, P prime is this direction. On the other hand, P1 prime is this direction. So it's just minus sign. Likewise, what we need to do is that so P2, sorry, K prime goes to P2, what I'm doing, P2, and then K goes to P2 prime. If you substitute this like this way, you can obtain this diagram to this diagram. That's called cross-section symmetry. That's called cross-section symmetry. So therefore, just plug that one into. Already erased. Sorry, I'm very sorry. I'm so stupid. I just erased here. Plug this one into the previous formula, so one can obtain the amplitude. And then I think I should explain Mandelstam-Barre more. This is cross-section symmetry. Let's stop after introducing Mandelstam-Barre. So once you evaluate this diagram, no need to evaluate this diagram from the beginning. Okay. So you just substitute like this. Okay, Mandelstam variable. So you have this kind of process. Have P prime, and K, and K prime. Then we call it that the S is equal to P plus P prime square, and T is equal to K minus P square, and U is equal to K plus P square. Of course, the momentum conservation will help. Unfortunately, I lost. So this is the called Mandelstam-Barre. So S and T and U. And if you take mass loss limit, it just becomes super simple. Okay, let me give me a few more minutes. If you introduce this one, so this one, if you and take mass loss limit, all the mass loss limit, for instance, mass loss limit, then what we have is that if you expand this one, this is equal to k squared plus p squared minus 2k dot p. But if you take massless limit, k squared and p squared is equal to 0. Okay. So therefore we will get 0 here. So here it's just massless limit. And the same thing happens, minus 2k dot p. 2k dot p. This is massless limit. And if you use this kind of variable, one can obtain that this diagram is equal to the this diagram is equal to 1/4. It's super simple. The sum of spin is equal to 8e to the fourth s squared t over 2 to square plus e over 2 square. Okay. So that's the it used to be okay. Let me give you an example. So it used to be something. It's written like sorry. So it used to be written like a 8 e to the fourth is square p dot k p prime dot k. I'm sorry, I erased plus p dot k prime and p prime dot k. So that is the massless limit. And as you can easily see, p dot k appear here, and k prime dot p prime dot k prime appear here. This is equal to minus 2k dot prime p dot prime, and this is equal to minus 2 p dot k prime p prime k prime. So therefore, so this term is t over 2 square and u over 2 square. And if you do this crossing symmetry, this is super easy. You just swap s and t, and this is equal to s and t. So therefore, this is 1/4 m squared sum over spin is equal to 8e squared t squared s over 2 squared plus u over 2 squared. Sorry, I just wanted to explain from this part. So you just cross symmetry is just you just swap s and t from left and right, t and s. So that's a cross symmetry. And then I think I should stop here. I was planning to relegate some of the one problem to next homework. So I will reduce one problem in the homework 4 this time, 4 to 5 or 4 to the next homework. So because you don't have so much time to digest this one. So yeah, I will change the I think problem 3 to the problem 2 or problem 3. It's both you need to use the Mandelstam variable, to be honest. Both. I think even problem 3 you need to use. Okay. Anyway, maybe I will relegate the problem 2 to the homework 5, so that you have some time to digest this kind of stuff. Anyway, so this time I will just postpone to the. I will explain a bit more detail next lecture. Okay. Let's stop here. Any question from the Tencent side? Do you have questions? If you have a question, just tell me. If not, I will stop the recording. Okay, I will